Hello guys, today we're just keep exploring logarithm, and today I'm gonna show you logarithmic functions, and that's sort of like nice function that you need to know how it works, how it goes, a standard function, and we also consider an inverse function. And you remember from previous videos that inverse function for logarithmic function is simply exponential function here. Alright, okay, so we start from normal logarithmic function y equals log a with the base a and of the number x, where a is more than 0, that's by definition, and a is not equal to 1. So I'll show you guys what if like we need to prove why, let's say a is not equal to 1. Let's say pretend that what will happen if a is 1. So just simply believe that if a is 1, we'll get the following: y equals log with the base 1 of x. And in this case, 1 to the power of y, by definition, how to restate this logarithmic equation into exponential form, we'll get y to the power 1 to the power of y equals to x. Okay, so what we'll get in this case, we'll get the following troubles, because here is going to be 1 always, and we'll get x equals 1. So in this case, we have only one single value for x, which is always 1. And it means that we can have any other numbers. So maybe for like specific example, it will be much more, clear for you. Let's say a is 1, and we have log with the base of 1, let's say 2. We want to calculate this value. Pretend that we don't know the value for that, but let's say log 1 with the base 1 of the number 2 is equal to some number that we want to find. And let's go to exponential form. We'll get 1 to the power of y equals 2. In this case, what is going to be? That's 1, because 1 in any power is always 1, will be equal to 2. So it's incorrect. It's incorrect, so that's contradiction, actually. Contradiction. And hence, we never say that a can intake value of 1. So for 1, it doesn't make any sense. So a is not equal to 1. Okay, so we recently proved that. Hope you understand. And we'll move next. So why a is more than 0? Because if it's negative, depending on y value, there might be like positive values and negative values for x. And that's actually impossible, because x should be strictly more than 0 as well. Okay, so that's why you have a more than 0 and a not equal to 1. However, there might be two like cases for a when it's like strictly more than 1, and let's say a is between 0 and 1. So we'll consider two cases, and first we consider the case when a is more than 1. And let's consider a specific example when a, let's say, is 2. And let's try to explore the function log with the base of 2 of x. Okay, so make sure you remember that x always should be more than 0. Okay, so what we're going to do? We're going to do the following. We can have an exponential form for, for technical usage. So 2 to the power of y equals to x. And from where we can set up the table for x and y values. So we just first start running like y through some specific values, and let's see what x might be in this case. So we just calculate an inverse way using exponential form. That's exponential equivalent form for our logarithmic function. Okay, so let's run y through, let's say -3, -2. We need to vary it with a step of 1, and 0, let's say 1, 2, 3. Okay, so what we will get as the x value? We simply start raising 2 to the different powers of y according to the values here, and hence we can calculate x values. Okay, just remember that a to the negative power n is simply 1 over an. That's from the previous video, you need to pick it up. And actually, negative power makes your number to be a fractional one. If it's fraction, just inverse fraction now, or reciprocal. Okay, so let's raise to the power negative 3, 2, and you'll get 1 over 8. We do the same for negative power 2 is 1 over 4. Negative power 1 to negative 1 is 1 over 2. 0, any number in 0 power will get always 1. Then 2, 4, 8. They simply reverse after 1. You see that? Okay, so that was there were fractions before, and now that reverse values. Okay, so we are going to plot all those values, and we start from x 1, 2, 4, 8. So 1, the value is 0. For y, that's the first point on our Cartesian plane or xy set. When x is 2, we'll get 1, so that's another point. When x is 2, when x is, 1, actually we need to, let's do it one more time. Let's check it. I messed up a little bit. Okay, so one more time. When 0, x 0. So when y is 0, yes, y is 0. X is 1, that was correct. Okay, let's set up the point. Because this is y set and this is x set. One more time. So 0, 1, then when 1 for y, we have 2 for x, so that's the second point. That was actually correct. Then for 2 for y, we'll get 4 here. Okay, let's set up another point. When it's 3, we'll get 8. So 8 is here, and we'll get for 3, 8. So it looks like your curve tends to bend towards x-axis, but however it's still rising. So we'll get still rising curve that goes in this way. All right, so that's logarithm. So when x is very close to infinity, I mean x like great numbers, your y also tends to have in infinite numbers, because it goes, there is no asymptote line for horizontal asymptote. There is no way to do that because y still be rising. However, the acceleration of this, like the change of rate, the gradient, it becomes like less steeper and less steep, so less steeper. All right, what about if you have negative values for y? -1, -2, so we'll have the following set of points. When y is -1, it's here, so we'll put 1 over 2. Okay, so when -2 for y, we'll get 1 over 4. So we every time be very close to y-axis, but we never touch that. So that's why your curve will go on very close to y-axis, but never touch that. There will be no intersection. So your final graph will look like a smooth curve that goes through specific points that we actually have them in the table, and that's your log graph. And we consider it when the base of log is positive, and it's obviously positive by definition, and it's more than 1. So okay, what if we have a simple, maybe just let's set up some properties and features of this graph. So first of all, what we discovered, the vertical y-axis, so y-axis simply becomes an asymptote. What this term means? This term means that this is the line where your graph approaches to when we have like tendency for, let's say, x to some value. In this case, the tendency, so y-axis becomes an asymptote. So simply it occurs when x tends very close to 0. And you see that your graph is very, very close to your y-axis. So basically, if it's like numbers for x, very close to 0, let's say x might be like 0, 0, 0, 0, like many zeros, millions of that, and somewhere in the end 1. This number is believed to be very close to 0, and hence your graph have the tendency to y-axis. Okay, so however, still like raising graph, and that's why for domain, it means x-axis, they're anything but positive. So x from the range, from the domain x more than 0. So simply to say x here to the range from 0 to infinity. Okay, x can never take the 0 value. It's very close, it might be very close, but it's not 0. Okay, what about the range? What about the range? I mean, y value, so that's the main. What about the range? So for range, we have y values from negative infinity to positive infinity. Okay? So that's why for the range, we have y from the set from negative infinity to positive infinity, means y is simply as any real number. Okay, so actually we came to the idea that x that stays here as a number in log cannot be 0. Let's pretend that x is 0. So let's say x is 0. What will happen? We'll get a to the power y equals always 0, and that's not possible because in this case a should be equal to 0, and for that reason y should be more than 0 strictly. But that's contradiction because we agreed to have that's contradiction, because contradict to the statement that a is completely more than 0. So remember we marked it before. Okay, so that's why a should be more than 0 and x can never be equal to 0. That's sort of proof. So that's again contradiction. All right, so that's why x can never intake 0 value. So what if we want to explore another type of the graph, and we'll just put it here. Let me see. So what we can get. So just want to use again Cartesian plane, and in this case we'll explore the function y equals log, let's say 1/2. Let's say the second case, we have the second case, a is less than 1 but more than 0. What we'll get in this case, let's say we have what a equals 1/2, and for a specific function we'll have that 1/2 of x. Okay, so one more time we can express it in the form of exponents, so that's why we'll get 1/2 to the power of y equals x, and again we can set up the values yx. Let's create the table. In this case I'll take less amount of points, 1 and 2. So we'll get for y the same set of points, just simply I shrink the range for y, and let's calculate what will x value be. Okay, -2, so we take 1/2 to the power of y, that means 1/2 to -2. It means we'll get, because again according to this formula, when we have negative power we simply reverse the fraction, we make it like it's flipped over, and that's why it becomes 2 to the power 2. So that means we'll get 4. The same here, we'll get 2. 1/2 in power 0 will get 0, and that here will get the same values but flipped. And let's compare what actually happened. There was 1/4 and 1/2, while here we'll get 4 and 2. They simply changed the place. So 1 is again the point where we doesn't have any change, and 2, 4 actually becomes 1/2, 1/4, and we'll get multiply 3, we'll get 1 over 8. Okay, so let's plot this graph. I mark it blue, so for this graph we'll have blue line. Okay, and let's simply mark all those points here. Okay, so we have -2 for y, and we'll get instead of so -4 instead of, yeah, so wait, we'll take -2 for y, it's here, and x is going to be 4. So it looks like we'll get that value. All right, so when y is -1, we'll get 2 for x, it's here. We'll get 0, we'll get 1, so that point will be the same. And we'll get 1 and 2 for y, we'll get 1 over 2, 1 over 4. So simply we'll have something like that points that are here. 1 and 2 is like even like close. So actually we build all those points and the graph simply behaves in this manner. Okay. So it looks like it's simply a reflection of your original graph. So let's have a compare with y equals log 2x in your graph, y equals log 1 over 2x. So what do you see, guys? If you put the mirror along x-axis, you simply will have a reflection. So because this curve will be reflected, and then how we can get the blue curve. So that's why that's for log 2x, and that curve for log 1 over 2x. So properties. If the first graph was rising, completely rising, in this case, the blue graph becomes completely falling. So when you move in positive direction of x, your graph, your y values are decreasing. So one more time about domain. Domain will be the same as for your previous graph. So range still stays the same. And y-axis also becomes an asymptote. However, the graph just becomes falling. So one more time to recap, if you see the graph, so like sort of quick summary. So if you have y equals log ax, so you need to state the first x not equal to 0, a, if it's more than 1, so the graph y from x is rising function, so it's rise. Okay, what about y equals log ax when a is from 0 to 1? So y from x just simply becomes falling function, it's falling down. And it's falling down on the whole domain. Okay, that was simply idea about the graphs. However, we'd like to explore the inverse function. Let's do it quick and let's see how it works. So let's explore inverse function for y from x equals log ax. So inverse function simply becomes a to the power y equals x, and then according to reversing rule, you just need to flip x and change with simply y. So in this case, you set up, instead of x, you set up y, and instead of y, you set up x in order to have like normal dependency y from x. So inverse function y from x simply becomes an exponent, a from x. And make sure you remember how it works with exponents. So for example, let's say for some definition, we have fx, like normal graph, logarithmic function is log 2x. What if we reverse it? We'll take the following, y equals 2 to the power of x, and that will be exponential form, that's exponent. In this case, how to build up an exponent. So this graph is completely rising, so that's why I just briefly make a sketch of your graph. That's an exponent. And so let's see what will happen. So to be honest, actually you can actually reverse the graph, right? For example, what if I just simply try to copy? Okay, we'll try to do that one. So I just want to simply copy that. Okay, so simply copy that. Okay, is it possible to copy? I think, oh no, it's only like past. I don't know why. So maybe let's try and do it here. Is it possible to paste or not? No, it's impossible. Okay, anyway, so we just make a sketch y from x, and we know that our log function, just remember the previous case, it goes like rising through the value of 1. That's log 2. Right now we're going to make a sketch of this graph. It's like rising this way. Okay, so that's a rising curve. It goes through 1. It has y as the asymptote, right? And let's drop inverse function, that's an exponent. So remember, reversing technique, simply if you use just simple graphing, what you need to do, you just need to drop the line, identity line, y equals x, and you simply need to reflect your log function in this line simply, and the reflection will look like this. Okay, that's one part of the graph, and this another part of the graph that goes this way. So this is an exponent 2 to the power of x, y equals 2, and here below is y equals log 2x. You can also check the values, so you just simply can plot the table y and x. So in this case it's much more convenient to plot first x, like set up the values and calculate y. So for example, let's run -2, -1, 0, 1, and 2. Let's calculate corresponding values for y. We'll get 2 to the -2 is 1 over 2, 1 over 4, yes, in total. And -1, 2 to the -1 is 1 over 2. Then 0 is simply 1. 2 to the power 1 is simply 2, and 2 squared is 4. So that's simply reversed. That's what you see for, for your log function, and hence the values that you're going to set up. Let's say 0 is 1, so 1 is here. When it's 2, somewhere here, it's going to be, when x is 2, it's going to be 4, like somewhere there. And when x1 is going to be 2. So looks like we will have the following set of points, and that's in full correspondence with what I made a sketch.